Hi guys, see you again in Chapter 6, Chemical Equilibrium. So, this is the third part of subtopic 6.2, which is we are going to focus on the degree of dissociation and reaction quotient. So guys, let's start. Alright guys, in this part, we are going to define and determine the degree of dissociation, and then we are going to deduce the expression for the reaction quotient and predict the direction of net reaction by comparing the value of A and K. So, this is the degree of dissociation, okay? So, definition of degree of dissociation is section of molecule dissociate or decompose into smaller molecules, ions or atoms. So, senang cerita kelas, degree of dissociation ni adalah kadar penguraian dia. Kadar penguraian, dissociate, terurai. Okay? So this is the formula of degree of dissociation. So the symbol of degree of dissociation is alpha. So the formula is change in concentration of reactant divided by initial concentration of reactant. So the simplest formula dia adalah alpha equal to X divided by initial concentration of reactant. So initial concentration of reactant. So ini semua you can find out from ice table. And then sometimes the question asks you to calculate the percentage dissociation. So the formula is same like this one, but kita hanya tambah times 100 only. Okay, so degree of dissociation, normally the value in between 0 to 1. If you get more than 1 or less than 0, something wrong with your calculation. And if the percentage, the value should between 0 to 100%. Okay, so this is the formula if you want to calculate the degree of dissociation. Alright guys, now we look at the example how to calculate the degree of dissociation for the substance. Okay, here you have the question. What you need here, you need to read the question first. Okay, take out the information given in this question. Okay, so dia kata dekat sini 0.024 mole sample of N2O4 gas allow. Okay, nampak ayat dia? Allow to come to equilibrium with NO2 gas in a 0.372 liter flask. Calculate the degree of dissociation of N2O4 gas. So, you can see here, okay, maklumat yang diberi adalah number of mole of reactant allowed to come to equilibrium. It means that this number of mole is initial mole. Nampak tak? Initial number of mole. Maksudnya dia baru nak achieve equilibrium. And then you have the volume of this system. And also we have the value of Cc for this reaction. Biasanya awak kira Cc, but now we have the value of Cc. Why? So kita akan tengok lepas ni. So kita ada mole, we have the volume. So what we can calculate here is, yes, the concentration. So awak boleh kira initial concentration of N2O4. Awak boleh dapatkan di mana mole divide by volume. Okay, so this is the initial concentration for the reactant, which is N2O4 gas. Okay, so we have the value of Kc here. So we can run the Kc expression first before we construct the ice table. Why we need ice table here? Because we need to calculate the degree of dissociation. Sekejap lagi awak nampak kenapa. Okey, dekat sini saya buat dulu KC expression. Okay guys, so this is the KC expression for this reaction. The concentration of product divided by concentration of reactant. Okay, and now we need to construct ice table. Okay, so this is our ice table. So it must consist of initial concentration, change in concentration, equilibrium concentration. So just now we already calculate the initial concentration of the reactant, which is 0.0645 molar. Okay, for the initial concentration of product should be 0. Belum buat apa-apa tindak balas lagi. And then change in concentration, we write it in unknown. So for the reactant, negative X. For the product, positive 2X. Ingat, negatif kadar pengurangan dia. Positif refer kepada penghasilan atau kadar penambahan produk. Okay, 2X. Kenapa 2X? It must depend on the balancing or the coefficient from this equation. Okay, so equilibrium concentration, kita akan tolak atau tambahkan initial dengan change in concentration. Okay, for the reactant, kita akan tolakkan dia. Okay guys, so now we have the equilibrium concentration for each reactant and product. But kita tak tahu the value of X. But we have the value of KC just now in the quotient. So, you can substitute all these things. Awak boleh masukkan semua ni dalam KC expression just now. Okay, so saya masukkan like this. Okay guys, so this one, kita dah masukkan all the equilibrium concentration for the reactant and product into KC expression. And we know that the value of KC from the quotient is 4.61 times 10 power of negative 3. And then you need to solve this calculation. Okay, so what you need to do, you kena selesaikan and then you kena dapatkan nilai X. So you akan dapat D nilai X. Okay guys, so kita akan dapat two value of X, X1 and X2. But which one you need to choose? Okay, you need to choose which value of X suitable for this equilibrium concentration. If you choose the X2, the value of X2 is negative value. So kalau you masukkan nilai ni ke dalam 2X ni, so you akan dapat equilibrium concentration for NO2 in negative value. Boleh ke equilibrium concentration ataupun senang cerita, boleh ke concentration dalam negatif? Tak boleh kelas. Okay, so this value of X2 kita akan ignorekan dia. Okay, tulis macam tu je lah. So kita akan ignore the value of X2. What we choose is the value of X1. Okay, boleh? Okay, and then this question asks you to calculate degree of dissociation. And we know that the formula is change in concentration, which is X, divided by initial concentration of reactant. So reactant kita adalah siapa tadi? N2O4. So saya terus buat so X divided by initial concentration of reactant. So ni initial concentration, and then we can substitute the value of X and initial concentration. Okay guys, so this is the value of degree of dissociation. So kita dapat nilai dia in between 0 to 1. Tak lebih 1, tak kurang daripada 0. So this is how you calculate the degree of dissociation. Okay, now guys, we need to predict the direction of a reaction. Macam mana kita nak tahu jika sesuatu sistem itu tidak capai equilibrium? So, macam mana cara dia nak achieve equilibrium? Okay, so the direction of a reaction can be predicted by comparing the equilibrium constant Kp or Kp with the value of reaction quotient Qc or Qp. It means that Qc you need to compare with Kp, Qp you need to compare with Kp. So, the expression for Q is the same as that for the equilibrium constant K. So, cara penulisan formula Q, Qc or Qp sama macam Kp and Kp. The reaction quotient is defined as the numerical value of the equilibrium expression. So, evaluated at any time, not necessarily at equilibrium. Okay, kalau Kp atau Kp, so the value of concentration and pressure should be at equilibrium. Do you remember? But for the Qc or Qp, the value of concentration and pressure, biasanya kita akan guna initial concentration or initial pressure. Okay guys, to deduce the expression for the reaction quotient Q and predict the direction of net reaction by comparing the values of Q and K. So this is the summary before we go to the question. Okay, for example, you have this general equation. Okay, we have the reactant A react with B, produce C and D. So if you write the Qc expression, this expression seem like Qc expression. So kalau you buat untuk Qp juga akan sama macam Qp. But the concentration involved here is not the equilibrium concentration. This concentration normally we use initial concentration. Okay, concentration awal bagi reactant and product. Okay. So, macam mana kita nak tentukan dia punya arah, direction, dia shift to the right or shift to the left. So, remember, you need to compare the value of Q and K. So, this is the summary. Okay, if you calculate the value of Q, okay, then you compare with K, you dapati Q less than K. Okay, the value of Q less than K, it means that the denominator, which is the reactant, is large relative to the product. So the reaction will progress to the right, it means that it will produce more product until the equilibrium is reached. Equilibrium reached when the value of Q equal to K. Macam ni lah kelas. Okay, contoh. Bila Q kurang daripada K, okay, so concentration of reactant akan meningkat. Nampak So bila concentration of reactant akan meningkat, macam mana kita nak balancekan left and right? Macam mana kita nak balancekan concentration reactant and product? Okay, contoh katakanlah concentration reactant kat sini 50. Contoh saya letak macam kita main duit lah. Okay, so concentration product dekat sini saya letak 10. Okay, contoh. Sekarang ni produk kita kurang. Okay, reaction kita banyak. So how kita nak balancekan dia punya concentration? So we need to shift the direction of this system, of this reaction to the right. Maksudnya 50 ni kena kurangkan, di mana dia bagi kat sini lagi 20. Contoh. So kalau dia bagi 20, 50 akan tinggal 30. Nampak? So kat sini 10 tambah 20, 30. So now your system balance. So sebab tu dia kata if P less than K, this system will shift to the right. Okay, why? Because the concentration of reactant larger than concentration of product. Jelas? Okay, next. If Q more than K, the reactant smaller relative to the product. So this reaction will progress to the left to produce more reactant until the equilibrium is reached. Maksudnya terbaliklah. Sekarang ni reactant kita akan kurang. Produk yang banyak. So bila produk banyak, reactant kurang. So sistem itu sendiri akan re-establish untuk shift the system to the left. Nampak tak? Okay, so awak bayangkan 50 ni duduk sebelah sini, 10 ni tadi duduk sebelah reactant. So dia akan shift to the left. Itu maksud dia. And then if the value of Q equals to K, so the reactant and product concentration or pressure has attained their equilibrium. No further net change. Maksudnya dia takkan shift to the right or shift to the left. It means that the system already at equilibrium. Okay, saya juga boleh bagi tips dekat sini. Awak boleh tengok simbol ni. Kadang-kadang pelajar lupa shift to the right ke shift to the left. Okay, this tips dia macam ni kelas. Senang je. Okay. So, kalau simbol ni buka, okay, mulut dia terbuka ke arah kanan, macam ni kan, ni buka ke arah kanan. So, yang ni kalau awak nampak, mulut dia terbuka ke arah kanan, it means that this system akan shift to the right. Kalau dia mulut ni buka ke arah kiri, okay, so dia akan shift to the left. Ini tips yang paling simple you can use when you answer the question. Okay, kadang pelajar tak ingat pun summary ni kan. Reactant lebih besar ke, produk lebih besar ke, tak ingat biasanya. So pelajar akan ingat cara yang paling simple lah. Okay, boleh. Okay, now guys, we look at this question. Okay, so how to calculate the QP or the QP. Okay, and then we need to predict the direction. Okay, so we read the question first as usual. So here in this question we have the value of QP guys. Dia dah diberi nilai QP, and also we have the balancing equation. And then in a given temperature, 1 atm of each component. Nampak of each component. It means that of each reactant and product is placed in a container. Okay, so daripada statement tu kita boleh dapati dia kata is placed. Place maksudnya dia baru nak dimasukkan dalam bekas. Nampak dia belum achieve equilibrium. So this 1 atm should be the initial pressure of each reactant and product. And this question asks you if the reaction at equilibrium. If not, which direction will it proceed? Nampak tak dia tanya? So, what we need here, we need to calculate QP. Kenapa kita kena kira QP? Sebab dalam soalan diberi QP. Okay? So, firstly, please write the QP expression. Okay guys, so this is the QP expression. If you can see here, the expression seems like QP expression. Sama je kelas. Okay, but the value of pressure here, not equilibrium pressure. If QP, the pressure that we use here should be equilibrium pressure. But here, we just use the initial pressure. Okay, just now we know that the initial pressure for each reactant and product is 1 atm. So we just substitute in this formula. Okay guys, so you can see here, this is the value of QP. QP juga tidak ada unit seperti KP. Okay, so this is the value of QP. We got 1.00. And then we need to compare with the value of KP. Okay, the value of KP a bit larger than QP. QP we have 60.6 while QP 1.00. So we can make a conclusion here. QP less than KP. Nampak QP less than KP. So this system is not at equilibrium. And we proceed to the right until the equilibrium is reached, which is the Q equal to K. So ini adalah cara awak buat conclusion dia. Boleh? Okay, next we look at this example. As usual, read the question first and take out the information given in this question. Okay, we have the balancing equation here, and then we have the value of QC here. So, a mixture of 1.57 mole of nitrogen, 1.92 mole of hydrogen, 8.13 mole of ammonia is introduced. Look at the statement. Introduced into a 20-liter reaction vessel. So, it means that this number of moles should be the initial mole. Nampak tak? Okay, sebab dia baru nak dimasukkan ke dalam bekas. Okay, so all these moles should be initial number of moles. And as usual, the question asks you to predict whether this reaction at equilibrium is not what is the direction of the next reaction. Okay, so if the question like this, kalau ada ketanya, is the system at equilibrium, so what you need to do, you need to calculate QC or QP. But here, we have the value of QC, nampak kita ada value QC, so kita kena kira QC. So nak kira QC, wajib ada initial concentration. Why? Okay, so kita buat dulu QC expression. Okay, so this is the QC expression. Okay, so kita ada concentration of product divided by initial concentration of reactant. And then here we don't have any initial concentration, but we have here is initial mole. And also kita ada volume. So, initial mole and volume, you boleh kira apa kelas? Yes, we can calculate the initial concentration for each reactant and product. Okay guys, so this is the concentration for each reactant and product. So note that to calculate the concentration, the mole divided by the volume in liter. So this is the formula of molarity. And then we have the initial concentration for each reactant and product. So we can substitute all these values into this expression QC. Okay, so this is the value of QC 2.36 times 10 power of 3. And then what we need to do, we need to compare with KC. Okay, so kita punya KC 1.70 times 10 power of negative 2. Here times 10 power of 3. So, yes. Here, if you compare the value of QC and QC, the value of QC more than KC. So this system is not at equilibrium. So dia akan proceed direction ke mana? Tengok ni, mulut ni Adam kata kan, kalau dia buka arah kiri, it means that the reaction is not at equilibrium and will proceed to the left until the equilibrium is reached Q equal to K. So this is how you calculate the QC and QP, and then how you predict the direction of the net of reaction. Okay guys, that's it for last part of subtopic 6.2. Bye! See you in subtopic 6.3.